So this video is going to look at polar covalent bonds. I want to talk a little bit about their definition, and then I'll give you the classic example of a molecule that is held together by polar covalent bonds, which is a water molecule. So with a polar covalent bond, what we've got is a situation where atoms are sharing electrons. So that's where the covalent part of this is coming from. However, they are not sharing those electrons equally. And so we're ending up with a situation where the molecule overall is polar. And what that means when we talk about polar from the standpoint of chemistry is the molecule has ends that are oppositely charged. So that's where the polar part of this is coming from. Now that we've kind of defined it, what I want to do is, again, give you that example showing you a water molecule. So a water molecule is, of course, H2O, right? And it's composed of 2 hydrogen atoms and a single oxygen atom. And I want to talk with this video a little bit about the structure of oxygen and about the structure of hydrogen as well, and why they want to come together to form these polar covalent bonds. So I have drawn out an atomic orbital model, a representation of what oxygen looks like. And you may remember that it has 8 protons that are located in the nucleus. So here's my little example of the nucleus, and to keep it simple, I just drew 8 plus, okay, meaning that we've got 8 positive charges there in the nucleus. And you may also remember from back when you learned atomic structure that all of these atoms that exist have, at least in their natural form when they're not ions, they have the same number of electrons and they have the same number of protons. So we've got 8 protons here in the nucleus. With oxygen, we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons that are floating around in those atomic shells or orbital shells. Electrons are negatively charged, and because we've got 8 positively charged protons and we've got 8 negatively charged electrons, oxygen as a whole, as an atom, does not have a charge to it. But it does have a different problem. So if you guys remember from back when we learned about electron shells and how electrons are actually assigned to these electron shells or atomic orbitals, you learned that the innermost shell, right, that's the one that's closest to the nucleus of the atom, can hold a total of 2 electrons. And once it's got 2 electrons, it's full. You also learned that the shells after that, so the outer shells, which are known as valence shells, can hold 8 electrons. And they want to hold 8 electrons because when an atom has 8 electrons in that valence shell, that's what makes it most stable. So oxygen's problem is it does not have 8 electrons. It has 6. And so it's not as stable as it could be. If you look down here at hydrogen, of course, hydrogen has just a single proton. So I've drawn 1 plus in here. And because it has 1 proton, 1 positive charge, it also is going to have 1 electron or 1 negative charge. So here's that single little electron, and it's in its innermost shell. And remember that innermost shell, the one that's closest to the nucleus, it can hold a total of 2 electrons, and then it's full. Hydrogen's problem is it has, because it's got 1 proton, only a single electron in that shell. So it really needs another electron in its outermost shell, which in this case is the first one, right? In order to be full and to be as stable as it can be. So what we see happening when we have oxygen and we have hydrogen and they are all trying to make themselves more stable by filling up their shells is we get a chemical reaction. And if you look at what has actually happened over here, the oxygen and the hydrogen molecules have bound together. And by doing so, this hydrogen is sharing one of its electrons with the oxygen, and this hydrogen is sharing one of its electrons with the oxygen. And because they're sharing, in a way, we now have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that valence shell, which is how we make it most stable. So oxygen is happy. But if you look at what's going on with hydrogen as well, before we talked about the hydrogens, they need 1 more electron, and then they're going to be full, they're going to be stable, that's what they want. And if you look at what's going on here, we have each of these hydrogen atoms that are sharing one of oxygen's electrons, and that really is giving them each a full outermost shell because they've got 2 in the shell. Here's where the polar covalent bonding comes in. So over here, we have a bigger atom, right? Oxygen is quite a bit bigger. Hydrogen is quite a bit smaller. We talked about the fact that this is a covalent bond type, right? It's polar covalent, so they are sharing electrons, but they don't share them unequally, okay? And the reason for this in chemical terms is because oxygen is a little bit more electronegative. I'm a biologist, so here's how I tend to explain it, and your chemistry teacher may hate this, but I think of these atoms, right, in a tug of war. Oxygen and hydrogen are fighting over these electrons that they're sharing, and oxygen is bigger, so it has those electrons more. And because it has the electrons more, the electrons are over on this side of the molecule more, and they are over on this side of the molecule less. So what we have now is a situation where we've got a positive charge of 8 kind of on this side of the molecule coming from those 8 protons, but we've got negative charges, okay, that add up to 10 on this side because usually the electrons are over here, and that causes a partial negative charge on that side of the electron. So here's our little symbol that you'll see written in chemistry that indicates a partial negative charge, that we've got a polar molecule because it's negative on this side because we've got a higher density of electrons over here. Down here, we actually end up with a partial positive charge because we have these 2 positive charges, but most of the time the electrons are kind of over here, and every so often they get down here with the hydrogen, right? Shared but not shared equally. So we end up with a partial positive charge on the water molecule. Anytime you have a molecule, okay, that again, its 2 ends are opposite, so we've got a partial positive charge on one end, a partial negative charge on one end. That's when we have a polar covalent molecule, or a molecule that's held together with polar covalent bonds.